let me tell you about this this application of TDA to dynamical fluids. But let me start. The problem is lateral convective flow. Lateral convective flow, maybe many of you know what is this, but if you have imagine that you have this cylinder full of water. Then from the down, we apply some heat. Then the water start to flow, and the temperature is try to equilibrate in all the volume. No? Okay. The problem here is to understand the behavior of the flow here inside the cylinder. There are some equations that govern the flow, but these equations are the Navier-Stokes equations, and they are very complicated to solve. No? Okay, these are the Navier-Stokes equations in cylindrical coordinates. The flow is characterized by three-dimensional real parameters. The first one is the Rayleigh number, which is this, the Prandtl number, which is this, and the aspect ratio of the cylinder, which is the height over the diameter, sorry. Fixing the Prandtl and the aspect ratio, there is an interval, I1 and I2, of the Rayleigh numbers parameters such that if the Rayleigh number is less than Ri1, there is no motion. That is because the temperature is not enough to begin the motion. No? Okay? If the Rayleigh number is between these two values, the motion does not depend on the time. That means that the motion is equal during all the time. And if the Rayleigh number is bigger than this or larger than this Rn2, the motion depends on the time. Okay, we are going to study the Rayleigh numbers between these two values. Now, because after the Ri2 here, when the flow depends on the time, it's a very, very complicated problem. There are no solutions, or there are not so much theory, any theory in this region. No? Okay, the goal of this project is to try to attack this case, but it's complicated right now. But we are trying in the future. We are going to try in the future. Okay, since we don't have solutions of the Navier-Stokes equations, the properties of this flow are studied with numerical simulations. The co-authors of this project made a very precise numerical simulation of the flow with a precision of 10 to the minus 8. In this article, they published this numerical simulation comparing with some experiments made in Holland. This is the experimental design. Here there is a cylinder with water, some cameras very powerful. Then they obtain these samples of the movement of the flow, and this is the comparison between the numerical simulation, which is in B, and the experiment, the data obtained from the experiment in A. No? Then we are going to use this numerical simulation to study the shapes of the orbits of the flow. No? Okay. These flows are important. Let me mention to you why these flows are important. There are many applications, but now here I'm going to mention only one application. This is the application: liquid metal batteries. A liquid metal battery has two liquid metals and molten salt between them. When the electrons goes to the device which is working with this liquid metal, also the positive charge move from one liquid metal to the other. And in this with this movement of the positive charge, the molten salts is heated. Then in A, begins the convective flow. No. Not exactly the vector field. The behavior of the Lagrangian orbit, the shape of the Lagrangian orbit. No. Okay. Then when the molten salt is heated, the liquid metal battery begins in the liquid metal A. In this part begins the convective flow. No, begins a convective flow. Convective starts in the liquid metal A, which wears away the salt layer. This is obviously these are images subtracted from internet. They are not mine. Then the flow here in this picture we can see how the convective flow is wear away the molten salt. No? And obviously, if when the two metals are in contact, the two liquid metals are in contact, a short circuit is generated, and the battery does not work anymore. No? Okay, so our project, the objective of the project is use TDA to study the shape of the Lagrangian orbits in the flow. I'm going to talk about these two papers. The first one is already published in 2022 in Physical Review Fluids, and the second one is recently submitted. My collaborators are José Núñez from the NES Mérida, the NES Morelia, sorry, Eduardo Ramos from the Instituto de Energías Renovables de la UNAM, Brian Hernandez, which is my master student and is here, and Carla Acosta, which is a PhD student with José Núñez. Okay, let me tell you about the first paper. We fixed the aspect ratio of the cylinder in 1.25 and the prime number in this number. Okay, we took 4 Rayleigh numbers in this interval, in the interval where the motion is autonomous, and we take these 4 Rayleigh numbers. Okay, the Lagrangian orbits are computed with the numerical approximation mentioned before. No, all is based in this numerical approximation, obviously. Okay, we have here the 4 cases, but let me mention to you that there is a symmetry in the cylinder. There is a symmetry in a plane that contains the axis of the cylinder, and then that's the reason why we only show the half of the cylinder, because there is a symmetry. Okay, the flow has a symmetry. Okay, that's what I mentioned. In the first project, we reduced the analysis to two dimensions, taking the Poincaré maps of the orbits in the middle of the plane of the cylinder. The plane just here in the middle of the cylinder. Here in this plane, we take the Poincaré map. Then persistent homology was used to quantify the properties of the sets defined by the orbits in the Poincaré map. Okay, let me show you the Poincaré maps. These are the Poincaré maps in the two cases studied. In the first one, we see that there is a laminar distribution of the flow in the 3-dimensional cylinder, but we are going to study only the sets in this Poincaré map. Okay. The centers in the Poincaré maps which are the black points in all the Poincaré maps, were computed with a precision of 10 to the -4. We apply TDA to the sets in the Poincaré map and compute 6 parameters. These are the parameters. Remember that the goal is to describe the geometrical properties of the Lagrangian orbits, then or quantify the geometrical properties, quantify with TDA. Then we use 6 parameters obtained with TDA or with persistent homology, more precisely, but not all of them. The first one is the average distance from the set to the center. Remember that we don't know any solution of the Navier-Stokes equations. Then this point, which looks like an easier orbit, is difficult to obtain. No, it's very difficult to obtain. Then the center is an orbit which we obtain only with the numerical approximation, with the numerical simulation. Okay, the average distance d bar from a set to the center is the first parameter that we are going to use. The persistence of the largest zero hole. Okay, you know that since the sets are in the plane, we only have 0 and 1 holes. No? Then we only keep the largest of the 0, 1 hole, or the persistence of the largest 1 hole. Okay, the number of clusters, which is the set in which the set is divided, that's the number of components. The radius of width and persistence of the final 1 hole, the persistence of the final 1 hole, and the number of 1 holes, and finally the sum of all the persistence 1 holes except the last one. Why these parameters? Let me show you how these parameters can describe some properties of the Lagrangian orbit. Okay, these are bars. These bars are obtained with TDA. These are the bars with the 0 for the 0 homology, and these are the bars for the 1 homology. And for example, observe that there are some numbers here. This is the number of components which are divided the set. And if we see the persistent the sets in the Poincaré maps, we can see that there are some sets which are divided in the islands, in segment islands, or which are some sets that which are segmented. Yeah. Okay, I can explain what is the Poincaré map. You have a cylinder. Then you can take the middle plane here, and we chose an initial condition. Then the flow, the numerical approximation start to begins. Then when the numerical approximation crosses the plane again, we keep this point, we record this point, and again we record this point, and again we record this point, and again and again and again. And all the points which are obtained in this way are the Poincaré maps. Yeah? Is there another question? No? Okay. Then, for example, observe that we have like a symmetry here, which is very, very sparable, very understandable because of the rotation of the, no? Yeah. No, this segment is not depending on the Z coordinate. Okay, obviously, yeah, maybe if we take the plane, yeah, we detect a different behavior, but here we detect all the properties of the flow inside the volume. No, not all the properties, because maybe in the corners there are some properties that we can catch with this, but okay, the properties that we detect in this plane are that we are going to study. Yeah, that plane is fixed. Yeah. Sorry, again? Yeah, the initial coordinates. Yeah, we take the initial coordinates or the initial conditions from the center from the point, this point in the center, to the center of the cylinder. No, to this plane in the cylinder. Yeah, here. The colors? Yeah, the colors, yeah, because I forgot to mention this. If we take an initial condition, all the points that are defined for this initial condition are marked with the same color. Yeah, I start in this point, and with different color, I chose some initial conditions, and I record all the points where this orbit cross the plane. Again, sorry. Yeah. No, yeah, they can cross. they can cross the initial two initial conditions never cross in all the cylinder, never cross them. Yeah, they never cross. Okay, then I don't know. Okay, these orbits which are segmented are okay. The orbits, there is a theorem here, not a theorem of these kind of flows. It's a theorem of Hamiltonian flows, but we already know that this flow, the Navier-Stokes flow, is similar to Hamiltonian in some regions, not in all the regions, but in some regions it's very similar to the Hamiltonian flow. And that means that the Liouville theorem, if you know what is this theorem, says that the orbits live when in this region where it is very similar to a Hamiltonian flow, the orbits are very similar to a torus. No, lives in a torus. No, then these orbits which are segmented are related to torus knots. No, torus knots are actually each segmented orbit, each segmented set of these determines a regular neighborhood of a torus. No, determines a regular neighborhood of a torus if the set has n connected components, then there is a regular neighborhood of an NP torus knot where P is between 1 and n. And we know that P is the number of jumps that we start in a component after a lap. How many segments jumps to the next segment which touch the orbit. Okay. Then these parameters can determine this flow, the properties of this flow. And in this case, for the second Rayleigh number, we detect two special sets. 9 and 10. There are more. For example, here 31. 31 says that this red set is divided in 31 segments, but obviously it's difficult here. But with the precision of the numerical approximation, we can detect this number on all these numbers. But these two, 9 and 10, correspond to these sets which are divided in circular islands. No, the circular islands, and obviously the TDA detect that they are special. These numbers are important too. But I don't know how much time. 20 minutes? Okay. Then, okay, I go to this case, that is the case with the Rayleigh number. In this case, the Rayleigh number is closer to the limit Ra2, where from this side, in this side, the flow is depends on the time, and this is the last one, and the last one that we study. And for this Rayleigh number, the flow looks like a very chaotic flow, no? And the numbers that we obtain, the parameters that we obtain, start to detect some order. For example, let me mention to you this case. Remember this bar corresponds to the last one hole, and when the bar begins or born is exactly when the hole is formed, no? And it dies when the hole is died. Okay, it dies when the hole is okay. Then that the persistence is too small of this bar, and this is the zero hole is large, means that these other numbers are important, but means that maybe this set is the more distributed in the space, in the plane, and that's the case. No, we start to detect some behaviors of the orbits, of the set of the orbits, no, which is very complicated because they came from the flow Navier-Stokes. But okay, I'm passing fast this part because I want to go to the three-dimensional case. which is the second paper, and 90 minutes is enough. Okay, we're going to apply the same idea, but for a three-dimensional case, but we need to change some things. For example, due to a problem of the parameterization in the center of the axis, because all of this was made with the cylindrical coordinates, but you know that cylindrical coordinates has a little problem in the zero, then we change to a cube. So we change the container to a cube. Okay. As in the cylinder, there is a symmetry in a plane that divides the cube in two equal parts. Again, there is a symmetry. Okay, maybe I have a. Okay, the orbits have more data. Okay, because we changed to 3 dimensions. Then we start to use now the alpha complexes. I didn't mention, but in the 2-dimensional case, we use the Vietri-Ribbs complex. No? Okay. And although the orbits and we use the Poincaré map. Okay, we use the Poincaré map only to explain, because it's difficult to understand the 3 dimensions orbits, but only to express where we take the the initial conditions or something. I'm going to use the Poincaré map, not only like a tool. Okay, this is an image of the flow. And there is a symmetry of the flow in the plane in the plane that cuts this. Okay, no. Yeah, this is the cube with the flow with the plane. Yeah, this is already the the region where we are going to study the flow. Observe that y is not to 0.1; it's only 0.5. Okay. Then these are the Poincaré maps. The Poincaré maps in the plane again, as in the last case, as in the cylinder, and these are we are studying only two Rayleigh numbers. Why? Because we already know what is going to happen here. This is very well known, but this is the one that which are interested in. Why? Because here we have these structures in 3 dimensions. Looks like nested toroid structures, right? Right? Yeah. Do you have a question or not? I can explain more if you want. Structure, yeah. Remember when we saw a circle here, and when the flow runs, reality this is an expression of a 2-dimensional torus, right? But if we take a circle inside, then we have a torus, but inside the white one, right? Then all of these, each circle here determines a torus when you take the 3-dimensional orbit, right? Okay. Then here we are interested. This case is very interesting for us because we have 2 nested toroid structures and some chaos between them. Then we want to understand the chaos between them. No? Yeah.
What are those gaps that occur?
Yeah, those gaps. It's actually these are perturbations of the flow. No. Also in Hamiltonian dynamics occur these gaps. And the theory says that these are perturbations of the flow. No, yeah, there is flow, but remember that we chose some initial conditions, and we don't catch this part. No, that was the reason. But there is flow inside of them, yeah. But you need to take an initial condition there. What is going to happen? For example, I don't know, the 3-dimensional orbit goes from this and taking another gap, and they're moving in between the gaps. Yeah? Are there more questions? No more questions? Okay. Then, we still take Rayleigh numbers where the flow is autonomous. The goal is to use TDA in order to capture a continuous evolution of the orbits, of the shape of the orbits. That's the goal. Okay, first we compare the persistent diagrams of the orbits, obviously. Then we compare the persistent diagrams with the bottleneck metric from an orbit to between the orbits. No. Okay. Then, for example, let me show what kind of persistent diagrams we obtain. For example, this is an orbit. This is an orbit which looks like a torus, no? And the persistent diagrams is this, obviously. This part is the part of the torus, the two one homologies and the two homology. But this part is a little curious, no? What do you think that is this part? Okay, I don't have so much time, but but there are three green dots here, no? Two homologies. It seems like there are two, but if you can notice, this green is so it's a little bit strong, no? That is because 2 points coincide, no? Okay, the reason is because this orbit is a torus, but like a square torus, no? And if I cut this torus with a plane, I saw something like this, like a square, because of the container. Then when we start to grow the radii, these points are joined before the diagonal, no? Then when these two are joined, the cavity inside the torus is divided in 4 cavities, right? Then that's the reason why this cavity of the torus is divided in 4 cavities just before die, right? Okay. And for example, this is an example of the orbits which are divided in circles, right? And the persistent diagram is something like this. No, something. It's exactly this. Okay. And okay, we already can understand what is happening with this, but it's not difficult to explain. But this one holds born when the points here in one between two parts here between two strings are joined, but all the orbit is not filled. Okay. Okay. The orbits have okay. In the first case, when the flow is laminar, the orbits have a natural order. Natural order, which is the average distance to the central orbit, to the orbit which we determine like a black point. Do you remember? Okay. And this is the formula when we obtain the average distance. Okay. The graph determined by this distance. Okay. All the orbits are compared with the central orbit, no? With the central orbit, which we denote gamma naught. And this is the graph. The graph is have a very predictable trend, and but observe that the trend is the same independently of the topology of the orbit, right? But if we want to apply TDA to detect the topology of the orbit and to detect a continuous evolution of the orbits, right? Then we apply the bottleneck distance with these parameters. This is the bottleneck distance between the two zero persistent diagrams of the orbit. 0.3 for the bottleneck distance in this zero persistent diagram, 0.1 and 0.6 for the persistent diagrams of the two homology, right? Oh, that is the reason why these coefficients is difficult to explain. We chose these weights or these coefficients by trial and error. Sorry? Yeah. But the coefficients are chosen by trial and error, and so there's some equal 1, only to catch what homology is the more important to order. But it's difficult to obtain an analytic formula to choose these parameters. It's very difficult. I don't know how. Maybe you can.
Let them be separate. That can give you more ability.
Yeah. These coefficients are determined by trial and error, but obviously we we have some explanations why these numbers, no? But we don't have a theorem. Okay, sorry.
You think if you in the idea, but with the part that is different.
Okay, it's because remember that this is only a numerical approximation, no? Then there are many, for example, these. There are many noise here, and in other orbits. There are many more noise and more points here, but the the one homology generates more noise. Then that's the reason why we use the less coefficient in the one homology. And for example, at the beginning, in this, we don't consider the zero homology because all the orbits are connected, but the flow has different speed in different regions of the cylinder. In this case, curve, no, have different speed. Then the points of the numerical simulation are more separated in some regions. Then this coefficient is due to the speed of the orbits. No, that's the reason why this is difficult. There are many parameters that you need to take in account to make this. No, more questions? Okay. Then now this is the graph or the graph, the plot with this distance to the central distance. No, notice that we can't detect the orbits with different topologies. No, the green ones have different are detected with this distance. Okay, but what happened in the case that we are interested in? No, here it's we have a problem because in this case there are two configurations of nested tori coexisting among them, and between them there is a chaotic zone. We take 100 watt initial conditions from this point from the center to the other center, and the goal is to to construct an algorithm which allows us to order the orbits in this region. No? Okay. Then there are two central orbits, and then we can define two average distance to the central orbit, to this or to this. No. Then first of all, these are the distances, the average distances. Obviously, we have a predictable trend in these regions, but in the chaotic zone, there is not a predictable trend. Okay, notice that in the chaotic zone, the average distance does not provide much information, and we begin to our metric or distance constructed with the bottleneck metric. No? Okay, from the previous case, we already know what is happening in the orbits and the tori structures, the nested tori structures. We already know the behavior of the orbit here. And okay, we start in the algorithm to order the orbit is the following. Okay, first of all, divide the orbits into groups. The group one are the orbits with the average distance closer to one of the center orbits. The group two is conformed by the orbit with average distance smaller to the other orbit, no? To the other central orbit. We propose an order of the orbits in the first group as follows. Using the DV, the metric which is we use the bottleneck metric, compare the orbit with the central orbit until the chaotic zone is reached with our initial conditions is gamma 38. From the remaining orbits in the first group, identify the one that minimizes the distance. Okay, in this region, we compare with the orbit in the center. But when we reach this zone, only in the first group, we start to compare with all the remaining orbits, and the one with closer distance is the following, no? And this is and we go on. Yeah? No questions? Okay. Okay. With this algorithm, okay. Okay. With this algorithm, you define a new order. In the second group, we do the same, the analogous procedure. With this algorithm, is define a new order of the 101 orbits. The results are presented with this formula. Let me show you the graph, because I don't have some more now. Okay, I have enough time. This is the graph. This is these are the orbits around the central orbit, the second central orbit. Let me call this. Let me know this. These are the orbits in the first central orbit, and now we have a very predictable trend of the orbits in the chaotic zone with this algorithm. But here, because of the trend, obviously the question is, what is that orbit? No, that orbit. Okay, the orbit in the peak plays a role as the middle orbit between the two central orbits, but the middle in shape, no, not the middle in shape, because right now we are comparing the shapes of the orbits. Okay, this is the middle in shape. This is the orbit which is the middle in shape. This orbit maybe is better make a draw. Okay, this orbit can be obtained in the following way. Okay, maybe it's not I'm not so good drawing. This is a torus. Okay, that not looks like a torus. Sorry. Imagine that we have two torus. Imagine that we have two torus. This is too thin, but okay. Then we place two torus in this way. No, the structure is similar to this. Two torus placed around this part. No. These structures are studied even in Mexico are defined. Jose Carlos is one of the specialists in Mexico. These kind of structures are called two stratifolds, trivalent two stratifolds, and we show that this has the homology of the two stratifolds obviously with TDA, with the persistent homology, and that's exactly this orbit, the orbit in the peak. This is an illustration of the formation of the orbit. The two blue orbits are the central orbit. Then the yellow orbit is how to the evolution that we capture from one central orbit to the other, and in the middle we take the two stratifolds. But I have a video. We finish with a video. Let me explain you. Can you pause? Let me explain you this video. We have two orders. So not exactly orders, the first one, but we have two orders. There are two toroidal structures, nested toroidal structures, and we chose 101 initial conditions from the center from one center to the other. And then the video begins because at the first part, the number of the initial condition, the order given by the number of the initial condition coincides with the order that we propose with this algorithm. But in this part, you are going to see the video in two parts. In the left, in the left is going to be the order that we propose with the algorithm, and in the right is the order which is given by the number of the initial condition. Yeah. Then, if you can see, the in the left is the order that we propose. No? Okay. Thank you. Okay, it takes how much time? Here we achieve the 2 strativolt. And the other side. And now we are in the other region, in the other netted toroid region, and it is exactly the same as the first of the video. No, then that's all. Thanks. Okay. Okay, I finished with that. Questions?
Back to the color, you said that each color is 1 micro-1%.
In the Poincaré, could you please put Control L? In the Poincaré maps? Whoops. If you want, I can explain it this way. Okay. What colors here in the Poincaré map? Here? Yeah? Okay. We chose initial conditions from here to here, and the initial conditions is marked with a color. No? Then the orbit goes to the orbit which is formed in the 3-dimensional maintains the color. Each orbit is associated with a color, and two different colors correspond to different orbits. No. For example, the orbits here, it's on the orbit which is a circle here. It's only a torus in this. No, never goes to this zone, for example. Sorry again. Yeah. It's dense inside the torus. Yeah. That's a very interesting question. What kind of torus knots appear? I bet that all the torus knots appear here. Not all the torus in this Rayleigh number. No. Actually, we studied that in the first paper that I mentioned, but we noticed that for a Rayleigh number there is a range, an interval of possible torus which are obtained here, but when we change the Rayleigh number, we define different intervals of torus knots. No? And I suppose, obviously, we don't have a theorem, but I suppose that in this range, for remember, a Rayleigh number is associated with a range peak with an interval. Let me show you T0 to T1. And I think that all the torus knots in this interval are possible to obtain. But this interval is determined by the quotient m over n. The PQ term is not PQ, and here is that is the quotient. Yeah, and I think that all the possible quotients are obtained, but I don't have a theorem. It's difficult because it depends on the precision of the measure. Yeah, because for example, a million times 3, or I don't know, maybe we don't have enough precision to detect a million of segments. No? Any more questions? Yeah. Okay, very good question, because as I said before, the numbers that we obtain here depends on the precision, and we use the cluster that they have in the Enes Morelia, which I don't know if it's so powerful, but I can tell you that so much time, I don't know, do you know how much time the numerical is running? I don't know, but what I can say is, remember that I have another collaborators that they are the specialists in this part of the article, of this numerical part. But what I can say you is that you can you can maintain the numerical precision for so much time, because the error is multiplying each time. No, then the error after some time, I don't know how much, but after some time, the numerical approximation is not comparable. No, you're welcome. Yeah. No, yeah. This is only to a tool to explain you, but the orbits are in R3, no? Then we consider an orbit like a point of close in R3, and we obtain we compute the persistent homology in this point cloud, which is an orbit of the flow. I don't know, 100,000 to 300,000. Yeah. This. More questions? No? Thanks. Thank you.